So here's a video about looking at the class overall and trying to figure out how to attack a problem that's given to you out of the blue. Because normally you're used to playing with problems that are in a certain section and you're doing the same thing over and over again. So here we go. In this class, there's times where you don't need calculus at all. There's times where you need to take a derivative, and there's times where you need to find an integral. So let's look at three options. So when are we not going to need any calculus? Well, whenever you ask for the average rate of change, that's not a calculus problem. All it is the slope between 2 points. Average cost, that's something that we play with every once in a while in this class. Just knowing that average cost is the cost divided by the number sold is important. Again, no calculus needed to know what the average cost actually is. Finding revenue and profit, of course, given that P is the price, little p, and C is the cost. The revenue is X times P, and the profit is the revenue minus the cost. So then the question is, all right, when do we need a derivative? And maybe more than one. Minimizing and maximizing is a big deal for finding derivatives. So when you want to minimize and maximize, it's all about taking the first derivative. You either set it equal to 0 or find where it's undefined. And don't forget those endpoints, because those might be maximums and minimums too. You're asked for the marginal cost. That's another time where you're going to need a derivative. So if you're given the cost, the marginal cost is the derivative. Slope of the tangent line. Well, that is exactly what a derivative is. The derivative is the slope of the tangent line. And another thing you might hear it called is an instantaneous rate of change. Implicit differentiation used with related rates. This is one of those word problem type things. The key thing with these problems is that they're telling you things and asking you about things with respect to time. This is going to be implicit differentiation. Now, I'm not going to actually do this problem, but realize the clue to knowing that this is a related rate problem is the fact that they've given you information about per week. A store can sell per week P dollars, and it's currently $85. It's increasing at a rate of $2 per week, and they're asking how fast is the number of watches the store sells changing per week. So that's that situation where even though the variable t is not involved, you want to go ahead and take the derivative with respect to t of both sides. Again, not going to finish this problem, but just giving you the idea. And continuing, there's a variety of other things where we need a derivative. We've spent a lot of times on derivatives in this class. Increasing and decreasing. So when is a function increasing and decreasing? Derivative is positive, increasing, derivative is negative, decreasing. Inflection points, you want to know where the second derivative, not the first derivative, the second derivative is 0. And just be careful, just because the second derivative is 0 does not mean it's an inflection point. Concavity, concave up means the second derivative is positive, concave down means it's negative. And then lastly, the question is, when do we need an integral? So sometimes we're given the marginal cost and asked for the cost. So again, we're not being asked for the marginal cost. We've been given the marginal cost. We're asked for the cost. That means that the cost is going to be the integral of the marginal cost. You got to find the correct constant, of course. Or if they care about producing from, say, 5 to 7 items, you want to go ahead and have a definite integral. You want to integrate the marginal cost from A to B. And then another way of, quote, seeing this or thinking about this is that you've been given the derivative and you're asked to find the function. That's exactly what's going on here. Another place that you're going to need an integral is area under a curve. Just remember that the definite integral is the area above the x-axis minus the area below the x-axis. And lastly, what about graphs? So let's look at the difference between these two graphs. They don't necessarily look all that different other than the fact that they're clearly different graphs. But look at the units. Millions of dollars is on the left-hand side. Feet per second is on the right-hand side. The right-hand graph has derivative type units. Derivatives are slopes. Derivatives are slopes of tangent lines, and slopes are fractions. So those units right there tell you that they're derivatives. Anyways, that's just a clue. So on the left-hand side, you probably need to take a derivative. I haven't put any sort of problem in here, but just the units tell me that most likely we're going to need to take a derivative. And again, that means the slope of the tangent line. A prime would have units millions of dollars per year. On the right-hand side, you probably, again, not necessarily because I don't have a problem here, but given the units, they're probably asking you to find a definite integral, I went ahead and integrated from a to b on my integral. And that's, again, the area under the curve. And that has units feet. This is clearly velocity because of the units. Velocity is feet per second. Remember that v is the same as the derivative. So you can also think of this graph. If you're given a derivative graph, then you're integrating the derivative. So I just, again, wanted to point out that if you're given a derivative graph, they're most likely wanting you to find an indefinite integral, which means you're finding the area under the curve.